Now let's look at an example involving the central limit theorem. Let's recall our notation for the sampling distribution of a sample mean. We had that the mean of the sample means is the same thing as the mean of the population, and the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. And this had a special name, the standard error of the mean. Okay, well, recall that we previously worked some problems involving the weights of adult men, and we found the probability for a randomly selected individual. So let's kind of redo that and see how the central limit theorem comes into play in our part B. So, the example was that the weights of men are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Okay, so this is what we've done before. We found the probability that a randomly selected male weighs less than 174 pounds. But let's go through those steps again. And so recall that we said we would sketch, label, and shade the curve. Get our normal curve here with our mean at 172. And we're interested in this value 174 or less. Well, trying to get a different color here. Here we go. So this is the area we're interested in, and we know that the mean, when we normalize our scores, on the Z scale, the mean is 0, and so what we need to find is the Z-score for 174. So Z, recall, is equal to our value of interest minus the mean over the standard deviation. 174 minus 172 over 29. And this came out to be 2 over 29, or about, remember to 2 decimal places, 0.07. So now we used our notation. Let's see what we wrote. So the probability that X is less than 174, well, that's the same thing as the probability that Z is less than 0.07. And this is where we used then our technology, and we said that on the, let's get another color here, normal cumulative density function, we put our low value here. Now we're going all the way down to negative infinity, and we said we would use -5. That's 5 standard deviations below the mean. -5 is essentially the same as negative infinity for our purposes, 2.07. And when we calculate that, we've done that on many times now, so I won't pull up the calculator, but we got 0.5279. Okay, and then we interpreted our results, and we said that there was a probability of 0.5279 There are many ways to say this, just as long as the information's there, of randomly selecting a man with weight less than 174 pounds. I guess they said male, so I can do that. A male with weight less than 174 pounds. Makes sense. We're a little bit past halfway. We know with the mean it would be 50% less than 172, so we're not surprised it's just a little more than 50%, or a 52.79% probability, or we could even say that about 53% of the male population weighs less than 174 pounds. But what we want to do now that's different is our part B. Part B says, find the probability that 20 randomly selected men will have a mean weight. You'll select 20, you'll add up their weights, divide by 20, and that mean is less than 174. Okay? So, can we use the central limit theorem for this? Well, we're using a sample size of 20, but remember, if we have a small sample and the original population has a normal distribution, that's what we were told in this problem. I'll just abbreviate that. So, the central limit theorem applies. Okay? So even though we have a small sample size, we're starting with a normal distribution, so we can use the central limit theorem. So let's sketch, label, and shade our curve. Here's our mean at 172. We've got this value out here at 174. And we want less than, so we want to shade this area here. Okay, so our x values are here. We'll find our z's. Of course, this is 0. And now we want to find, but this is, I'm sorry, these are our means, x bar, because we're saying we're going to take these 20 men, we're going to add up their weights, divide by 20, and these are going to be means. So their mean weight is less than 174, right? So now let's calculate the z-score for an x bar of 174. So I'm going to write that down. Calculate z-score for a mean weight of 174. Okay, so let's get the formula for doing that. Z equals x bar minus the mean of the sample means over the standard deviation of the sample means. Okay, but now what do we know about that? This is our x bar minus mu, because remember we said these two are the same, over, and now we'll use our population mean over the square root of n. And here's where you have to be very careful how you put this in the calculator. If you don't put parentheses around this, it won't understand what you want. If you want this fraction to be in the denominator, you're going to need to put parentheses around it or calculate it separately. So you can see I'm not going to get the same answer that I got when I worked the individual, when I randomly selected an individual. The numerator is the same, but I'm dividing by something different. It's not just sigma, it's sigma over the square root of n. So it won't be 0.07. Let's see what it is. So z equals the mean weight we're interested in is 174. The population mean is 172. It's also the mean of the sample means, divided by the standard deviation, which was 29, over the square root of 20. Okay, and now when you run that calculation, you get 0.3084, but I know z-scores go to 2 decimal places, so that's 0.31. Remember, we had 0.07 last time, so 0.31. The results are not the same. These are not the same problem. We're finding the probability of a sample having a weight less than 174. Okay, now let's use get our notation here. So, the probability that the mean for these 20 males is less than 174, well, that's going to be the same thing as the probability on our normalized scale that z is less than 0.31. So we still now can go to our function, normal CDF. Again, we're going to negative infinity, so we'll use our -5 standard deviations away from the mean, but now it's 0.31. And that comes out to be, what, 0.621719, or approximately to 4 decimal places, 6217. Okay, so our interpretation now is there is a 0.6217 probability that a sample of 20 men will have a mean weight less than 174 pounds. Okay, we got a different result when we considered a sample because our calculations are different. We're using the central limit theorem here because we're talking about the sampling distribution of a sample mean, not just an individual measure or data point, but a sample mean. So keep in mind, here's the difference, and often these problems will have an A part and a B part, where the A part, you're looking for that individual value, and it's all about the Z calculation now. The individual value, Z equals X minus mu over sigma, right? Or the B part is often the sample value, and here we need to use Z equals X minus mu over sigma over the square root of n, and do not forget those parentheses. Okay, that's what you need to get from this in order to work these problems. This is for the sample, this is for the individual.